Okay, so you can think of this as a definition of a surface. And what does this mean? So, I mean, the surface that we are all familiar with is a sphere, right? Because we live on one, right? And so here you know that if you take a point, if you are a little ant or a human on the surface of the Earth, a point around you is homeomorphic. If you look at an open disk, right? It looks like an open disk on a plane. This guy is a homeomorphism F from this here to R2. We can, just like an open unit disk is homeomorphic to R2, right? So what you see around you when you think of, well, earlier, I mean, humans did think that the Earth was flat, right? So this looks like a plane. And so this notion is sort of something that we are all familiar with. And the same thing happens on a torus, right? So on a torus, you would see that, you know, sort of locally you have things which are homeomorphic to R2. All right, so something which is not a surface is something where maybe where if you think of if you two spheres, let's take two spheres touching at a point. Yeah, maybe not intersecting. There's some point and you have two spheres touching there, right? So now if you are an ant at that point, you won't see a single sort of a plane around you. You'll see something funny, right? There's something else that is coming in and hitting you. So you have it's sort of branching off. There are two things where you can sort of go, right? So that's not homeomorphic to R2. Okay, so this is not a surface, and you can come up with many examples, right? So I mean, you can so something which is not a surface. According to this definition, something which is not a surface is a Mobius strip, also, right? Or a disk, right? So a disk is not a surface because you have a boundary, right? So you have a sort of boundary edge. So if you're sitting on the boundary, if a point on the boundary locally looks not like R2, but like half of R2, right? It's just, you know, like the upper half plane, and there's nothing on this side, right? That's not homeomorphic to R2. So this is locally, it's a half plane. It's not the full plane, it's a half plane. And these kind of things are not surfaces, but a surface with boundary. Okay, this is called a surface with boundary. So called, let me just say it's called surface with boundary. So a disk is a surface with boundary, and a Mobius strip, also a Mobius strip, a cylinder. These are surfaces with boundary. They're not surfaces in the definition I gave, okay, which is this definition I guess is basically something without boundary, right? And so it turns out that, so for surfaces, so how do you tell whether surfaces are homeomorphic is completely understood, because you have these topological invariants like Euler number and orientability, right? So, so we've already seen a classification theorem of surfaces. This tells you that that the Euler number. So this is actually, I should say, this is for closed surfaces. So so these are so closed means it's no boundary, as in the definition of a surface. Maybe I needn't have mentioned that. And it's also compact. Okay, so if for people who've already seen what it is, you know it. So the compact avoids things like, you know, some cylinder, something like an infinite cylinder. An infinite cylinder is something that goes off, you know, for ages, right? It has no boundary because somehow this, you know, you're at infinity, boundary is infinity, but it's not compact, okay? So but if you are like something like a sphere, then you are bounded, and, you know, so it turns out it is a closed surface. And it turns out that if you Euler number and orientability are these two topological invariants, that so this and this is a, let me say, it's a complete set of topological invariants for closed surfaces. That means that if your topological space is a closed surface, right, you have two closed surfaces, and you know its Euler characteristic and orientability of both, then you can tell whether it's homeomorphic or not. Okay, so so usually Euler number equal doesn't tell you that they are, some topological invariant equal doesn't tell you whether they are homeomorphic, right? So if they're not equal, then you know that they are not homeomorphic. This it follows from logic of being a topological invariant. But in this case, for closed surfaces, Euler characteristic and orientability, once you know these two, then you actually can distinguish. If two things have the same Euler characteristic and they both are orientable, then they're actually homeomorphic. Okay, so this is the theorem. Which, so the proof of this, once you sort of go through, let's say, one semester's course of topology, you would be able to find. So you would be able to understand. It's not that hard, but it does require some work. It also extends. You also have versions for surface width boundary. Okay, so if you have a surface width boundary, you might have to count the number of boundary components, right? So the connected pieces of the boundary and so on. Like a cylinder will have two components, while a Mobius strip has one. So you already know that somehow you know that this cylinder and Mobius strip cannot be homeomorphic and so on. So there is a classification for that. So for surfaces, somehow this basic problem of topology is quite well understood and is kind of solved. One set of topological spaces or some question in topology where it is not solved is about knots. Okay, so this is where so let me sort of now come to a little bit of knot theory. Okay, so this is sort of it's been an ongoing area of research for more than 100 years because this is still unsolved. Okay, so what is a knot? Okay, so a knot is an embedding. So it's a continuous, let me just say, it's a continuous embedding of a circle, which is, so a circle is usually denoted as S1. Okay, so it's sort of the sphere in one dimension, right? So the circle into R3. Okay, so so what you should think of is that so mathematically how so let me just say how you would another way of thinking about it. That is, you have a map from the circle to R3 that is continuous. And what does embedding mean? Embedding means it's injective. Okay, so this is how you can think of it. So it's a continuous and injective map from a circle into. So this is how you would imagine. So I forgot to get a shoelace or something, but you can imagine that you have some sort of, so this is my sort of string, and you can so you can sort of do something to it and then sort of tie up the ends, and then and so what would happen is this whole curve is topologically it's a circle, right? But you're putting it inside R3 in a different way, right? So that's a knot. Maybe let me draw pictures. So let me sort of instead of trying to demonstrate. So let me sort of draw some. So there's the simplest knot is the unknot, where you just have a circle embedded in R3. Okay, so some kind of standard. Let's say you're an XY plane, and you are sort of putting the circle as an actual circle on the XY plane in R3. Okay, and so let's say this is the sort of the other Z direction. So that's an unknot. You haven't really knotted it at all. Okay. What is an example of? So simplest example of a knot, which is different, is the trefoil. Okay. So so let me try to draw it. So the trefoil knot. This looks like this. So somehow, so you have this. This this. Okay, so this, you can imagine this. So I'm drawing this thing, how it sits inside, three-dimensional space, right? So you have this, some of these arcs are going behind and some are in front, right? Now this guy, okay, so this is how one sometimes ties shoelaces, so it's the simplest knot, you just sort of loop one and then put it in the other. And there's another way of getting the trefoil. So let me actually sort of demonstrate that. So this is again going back to the day we looked at Mobius strips and so on. So here's a strip of paper. I'm going to, so remember that the Mobius strip was made with 1/2 twist, right? So you have so you kind of, so this would give you a cylinder, right? But if I twist it, by 180 degrees and then glue, that would have given me a Mobius strip. So now what I'm going to do is I'm going to do 3/2 twists, okay, and glue it. So let me do that. So let me try to, so I'll put some glue here, and then I'm going to do, let me just try to show. I'm going to do 3/2 twists. So 1/2 twist, and then 2, and then 3. Okay, and then I'm going to glue these. Okay, and then, oops, I hope this stays. Right, so this is my sort of this is a 3/2 twisted strip. Okay, and now, so what happens when you cut this in half? Okay, so so let me ask you folks first. First of all, yeah, let me ask you whether, do you think it will be, after when you cut it in half, will it give you one connected strip or 2? Okay, so yeah, so it will be, well, yeah, so people are guessing right. It's because, we saw this when you look at the diagram, right? So when you sort of, you did one flip, you got connected. If you get 2 flips, then so topologically the surface you get is homeomorphic to a cylinder, okay? And then you would get, when you cut a cylinder in half, you get 2 components. But if you now do another flip, then if you look at the diagram, it will look again like the Mobius strip. So this guy is homeomorphic to a Mobius strip, okay? It just looks, it is embedded in a different way in R3, okay? So if it's homeomorphic to a Mobius strip, if you cut it in half, it will still remain connected. So, but the thing is that since we are, in R3, it is different. We'll get something slightly different now. So let me, slightly different than what we got when we cut a Mobius strip into half. Okay, so let me try this. I hope I did 3/2 twists actually, so I forgot to check. But we'll find out, right? So if it connected, then I certainly did an odd number of half twists. Okay, so right. Oops. This is slightly trickier because it's more twisted than a Mobius strip, so it's somewhat harder to cut. Okay, so we're getting there. Any guesses of what one would get? I mean, why I'm showing you this? You can type in the chat. Okay, so we are almost there. Right. So, yeah, so what you get is connected. All right, so it's not breaking up into 2 pieces. If you look at this, if you follow one of these strands, it's going to come back. But what you get is actually the trefoil knot. Okay, so it is it's embedded in R3 as a trefoil. So it's kind of, yeah, you have to, since this is paper and all and not string, you might have to imagine how this guy, whatever I did, is it looks okay. So I should have taken a longer strip, but this thing, whatever this is, you can. Did somebody say something in the chat? I see some. Yeah. So, Sarvesh, do you have a question, or what is the? I didn't understand what you typed in the chat. In any case, so this is a connected thing, and you get a trefoil knot. Okay, so it's a knotted thing. So this is one way of getting the trefoil knot.